maximum complexity may be achieved on symmetric functions.
Yes.
Did you try to compute A6 under this conjecture?
Trying to think if that conjecture would help me. See, the thing is, if you're building a symmetric function, there's no guarantee that the two subpieces are symmetric. And so you still have to kind of enumerate all the non-symmetric subpieces. So I don't actually think that would help me compute it.
And for the second sequence, can you go back?
Sure.
So my question is, so probably by combining two smaller DFAs,
Yep.
you can get a DFA
Yes.
for certain n.
Yeah, so that would give you an upper bound as well.
Did you try to see what would be upper bound for M13 if you combine smaller?
Well, I have an upper bound from their thing. The combination only works for, I think if you fix the formula. I don't think it works over all formulas. I think the quantifier gets in the way. So if you think about just parity, right? Like in 2001, someone should have pointed out that n equals 5. If parity for n equals 5, you could build from parity for n equals 2 and n equals 3 and have two copies of each. So that's only 3 plus 6 plus 3 plus 6 plus 1, which is I think 27, which broke my thing. Sorry, this isn't the function one, but you can build it, but again, the quantifier gets in the way. John.
I take it that really these computation-heavy things means using the known ways of computing things.
Yes.
You don't have any proof that, of really lower bounds for computation.
No. I have no proof that this requires. If you came up with a proof for why the sequence is what it is, then it might just you just sit down and calculate it. No, these are computation-heavy because I'm ignorant.
So, for instance, the answer to some computation-heavy thing might actually be 1, 1, 1, 1, 1, 1, 1,
Sure. Yeah. I mean, the Collatz thing is computation-heavy.
But the circuit complexity,
Yes.
you do monotone circuit complexity without negation?
We thought about doing it, but I never did. I think it's much easier. I think it comes out.
Yeah, you should probably crank up.
Yeah.
I have a sequence, it's in my coinage game, that in this sense is computation infinite.
Okay.
Which is, if some people will know the coinage game, I can't define it right now, but if you want to know whether a certain integer is a good first move or not in the game, then we actually know the answer for n below 16. But at 16, we don't know the answer. We know the general function is a computable function, because it's very interesting that the proof of that doesn't give an algorithm. It just says there is an algorithm. And for 16, it's one of my problems that I offer $1,000 for a solution, whether 16 is a good first move or not. That problem's been open for about 40 years. We don't know. Nor do we know any way of finding out.
Any other questions? Okay, let's thank Russ again.
Thank you.